Okay. So, well, good morning, everybody, and thank you for attending this webinar and listening to me. So the subject is how to take a proactive approach to voice performance management. So, what do we mean by proactive? So, back onto what does proactive mean? So, reactive is nightmarish. It's basically when users report problems, you have to try and locate them and resolve them. You may not be aware of problems before users report them. So this creates time pressure to fix issues quickly because they're already affecting people. And the other aspect of this is that users often don't report isolated problems, but get annoyed if the problems persist. So in other words, a problem may have existed for some time before you get to hear about it. So all this is not good. The proactive approach is to detect problems before they impact users, detect problems immediately as they occur, and so this allows you to do earlier troubleshooting with less firefighting and fewer annoyed users, and overall this improves the reliability of the service. Problems do occur, but if you can find them quickly and troubleshoot them quickly, then overall you have a better service quality. So there's two approaches to proactive performance management, so I'm going to talk about both of them. First, the active testing and then passive monitoring. So with active testing, you do periodic synthetic tests, so artificial tests, to verify the network and infrastructure performance. These could include testing IP paths, making synthetic voice over IP or video conferencing calls. And the idea behind this is that you can detect problems before they impact users, because this can run overnight, and also alert telecom or IT staff immediately if problems detected. Passive monitoring is the counter to that, which is you're monitoring live traffic. So you monitor every voice over IP call that's made. You collect reports in real time. You automatically identify calls with degraded quality, and this allows you to detect problems that did affect users, but you can detect problems before users complain about them. And again, you can alert telecom and IT staff immediately a problem is detected. So with a combination of both of those, then you can detect some network and infrastructure problems before they affect anybody. But if they do affect people, then you know about it instantly as happens, and you've got some good diagnostic data to start working with to troubleshoot the problem. So factors affecting call quality, there's quite a few. So there's the type of voice codec that's being used, the bit rate that the codec is running at, and also the audio bandwidth. Traditional telephony is narrowband. We see a lot of wideband voice today. There's also super wideband and full band even codecs. So those all affect the codec aspect, the encoding aspect of the voice quality, and then the packet loss rate. Obviously, if packets get dropped in the network, that's going to cause gaps in speech, which the voice over IP equipment will attempt to repair, but it will cause some degradation in quality. If jitter occurs, then a small level of jitter doesn't really do too much, but if the jitter level increases, then packets can end up being discarded by the receiving end IP phone or gateway, and then they essentially appear the same as a lost packet at that point. So what you're really interested in there is the packet discards due to jitter rather than inherently jitter itself, although jitter is a good sort of warning parameter. Then round trip delay, which includes the network delay itself, but also the end system delay. And so the end system delay is the amount of time it would take from when a packet arrives at an endpoint, like an IP phone. It goes through the jitter buffer, which is intended to minimize discards, gets decoded and played out, and then there's the corresponding speech in the other direction would be encoded, packetized, and sent. And so that kind of loop time to go from the received packet coming in to when a corresponding packet would go back out again is referred to as the end system delay. And that can be quite important. So, for example, in mobile networks, people quite often use very large jitter buffers because you can have more significant levels of jitter. So you make the jitter buffer bigger in order to accommodate a higher level of jitter. But the problem is this then increases the amount of delay. And so eventually, if you make the jitter buffer big enough, then it's going to cause conversational problems between the users. And then there's also signal level, noise level, and echo are factors as well, although one's not always in a position of being able to measure those on live calls. So when we talk about voice quality, we take those parameters and we put them together to produce some sort of a high-level metric to give us a view of what the call quality is. And typically in the industry, we use MOS scores, which is a mean opinion score. So a MOS score is a 1 to 5 scale, where 1 is unacceptable and 5 is excellent. So most voice over IP calls have a MOS in the range of 3.8 to 4.2 as typical. If the MOS goes down to 3.4 to 3.6, then it's slightly degraded. When it gets down into the 2s, then it's definitely severely degraded. And if it gets much below 2.5, then the user is probably going to hang up. There are actually not just MOS score. We also talk about MOS LQ and MOS CQ. So MOS LQ is listening quality MOS, and so this takes into account the codec type, loss, jitter, and also the burstiness of loss and discard. And MOS CQ is the conversational quality MOS. So this also takes into account the delay and also echo if that's available. And so between MOS LQ and MOS CQ, it gives you a good high-level view of what's whether the call is acceptable or not. And so if that's low, then you want to start to drill down into the underlying parameters to find out what it is that's causing it. Now, one key thing that to note is that network problems are typically transient. You're dealing with IP networks with routers and switches and traffic going in different directions, and so the impairments that affect voice traffic going through the network are typically time varying. And the net result of that is that call quality itself is time varying, which means that the call quality estimation algorithm, which is the algorithm that takes all of those individual factors and produces the MOS score, needs to consider the time varying nature of quality. The most widely used algorithm that does that is VQMOD, which incorporates a perceptual model that understands time varying quality. So now let's talk a bit about active testing. So active testing uses synthetic transactions to emulate traffic in a network. So for example, you might want to test a web server. So you do an HTTP GET from the web server. Or you may want to do email. So you could do a POP or SMTP transaction with an email server. Or in our particular case, we're interested in, well, the subject of this presentation, you may want to do a synthetic voice over IP call. So you'd want to have the agent, which is the thing that originates the synthetic transactions, to act as if it was an IP phone or a gateway and make a call, basically. And in the process of doing that, it's going to run tests against the servers, infrastructure systems, and the test call could be between two agents, or it could be between an agent and a gateway or phone. The good thing about this is it gives you complete control over call and session parameters. So if you suspected that the problem, there may be a problem because of the codec being used was very high bandwidth, or the jitter buffer settings you were using in your devices were not right, those kind of parameters, then with active testing, you can actually experiment with those and see if you can improve quality by changing things. So, and also the fact that you've got very predictable call timing and parameters makes troubleshooting more practical. Otherwise, you have to get a user to make a call at a particular time so that you could find it and look at it. But with active testing, you can say, okay, now make a call from here to there, and it'll the call will happen nearly instantly, and you'll get the parameters back in 30 seconds or a minute. So it makes troubleshooting more practical. So active testing is typically used in 3 different ways. One is pre-deployment testing. So this is basically verifying that a site or a location or a campus is able to support good quality VoIP connections before you actually deploy anything. And so you could do a single call if you're expecting a location to have to support 100 simultaneous calls. Then you can synthetically generate 100 simultaneous calls and verify that everything seems to work okay and that the performance is acceptable. Then second approach is continuous monitoring. And so this is typically run 7x24 with short tests at fairly short periods, like every 5 minutes or maybe every 15 minutes. And so the idea is to have minimum impact on the network and infrastructure. But so you don't really want to load it down, but you have this sort of very short cadence, and so that way, if a problem does occur, then you can detect it fairly quickly, and then and then get alerted to know that you need to go and troubleshoot that. Then the third area where active testing is used is troubleshooting. So given that you've either from active testing or from passive monitoring, given that you've identified that a problem is occurring, then active testing is a really good way to be able to start to troubleshoot things. You can get trace routes from remote agents. You can make test calls to devices that appear to be having problems, and you can really get into doing problem diagnosis. So as an example, then if we have 3 active test agents, then what they can do is they can make calls between each other or to IP phones or gateways. So they use SIP signaling to make the call, and then if the SIP call establishment's successful, then a media stream gets set up. And so through doing this, you're actually testing both the SIP infrastructure, which is the registration process by which an agent or an IP phone periodically registers with the SIP proxy or registrar to make sure that it knows where to find it. And then the call setup process, where it sends a SIP invite to request a call to another agent or phone. And then, given that the call setup's successful, then you get RTP streams initiated and send media backwards and forwards and measure the quality of those. So you can test out do a fairly good test of the voice over IP infrastructure using active testing this way. And so the various aspects of the network that are exercised in the process of doing all of this, DHCP assignment of IP addresses. So typically the agents would follow the same rules as any other IP device in terms of IP address. DNS lookup of the proxy name, correct operation of the SIP proxy, and then the ability of the network to support good quality media. So make sure there's not any excessive loss or jitter. Test the ability of the network to support the expected volume of calls. And also, it's quite common to incorporate a trace route into the test itself. So that way, whenever you do an active test, you also have a trace route of the path taken by the media during the test. So a typical deployment model for this would be that you would have, so you have a core of the network, and then you have a number of sites. The sites have IP phones on them. Then you can have agents located on the sites. There's small software agents, and they can make calls to each other or to an agent in the core of the network. And this can be, constantly being used to check things out. And then the results of those tests go to a management application that's receiving those and thresholding them and detecting if there are problems, and then alerting people if there are. Okay, so now passive monitoring. So the idea behind passive monitoring then is we want to monitor every call. You could, some people have argued in the past that, well, surely you only need to monitor the bad calls, but that presumes you know what they are. But it's good to have the distribution where you have good calls, you have bad calls, and you can compare the two, and you've got complete data on the service. So you monitor every call, and you keep a record of the data that you got. So we sometimes call that a call quality record. And so we get that, put it in a database, and then we can analyze it. So those call quality records can be analyzed in real time. So literally, as the report arrives from the network, from the device or from a probe, then as that report arrives, then you can threshold it. And if it indicates there are problems, then you can generate an alert immediately. So that means that these reports are typically sent at the end of a call from the device or a probe. So that means that you know within seconds of a call ending that call had issues. But also the database of call quality records allows you to troubleshoot completed calls. So not atypically, if somebody was having a few issues, but they weren't really that horrible, then they may say, oh, by the way, I was using the phone, so I was calling this other location on Tuesday, and there were some problems. We're having issues getting calls set up. The the call quality wasn't very good. And so because you have the database of call quality records, you can actually go back and look at exactly that. You can find the calls that were made at that time between that point, and then you've got good data to start with trying to understand what the problem is. But also it allows you, if you've got if individual users, if your frequency of phone calls from an individual user is not super high, then maybe the same problem is affecting this user now, and then the same problem affects a different user in an hour's time and a different user after that. So each individual user may not be necessarily very troubled by it, but it's occurring fairly frequently in the network, and so the idea, because you have a database of call quality records and you can correlate things in real time, then you can recognize that these problems are occurring across users, and then get alerted and get into troubleshooting. So there's several different approaches to passive monitoring. So we have an IP phone that's making a voice call. So one thing we can do is the phone itself can incorporate voice over IP performance monitoring, and then that can generate call quality reports directly from the phone during the call and at the end of the call. So one of these is the SIP publish message, which is I'll explain it a bit more in a minute. And so the phone can gather useful performance data, put it in a SIP message, and then send it through the SIP infrastructure back to the performance management system. There's also another protocol, which is called RTCPXR. And so this is used, and again, I'll explain it in a minute, but this is sent more frequently between an IP phone and its counterpart, another IP phone or a gateway. And then you can also have a probe that can measure quality by monitoring the media and signaling stream. And these are to some extent independent. So you could use phones that generally support the SIP publish message and don't use a probe, or you could use a probe and with a phone that doesn't support the SIP publish, or you could use both. So you can do any mixture of these different things. So let's dive a little bit into what these are. So firstly, then the idea is you have an embedded call quality agent in the phone itself or in a gateway. And so what this is able to do, this is able to look at the received media stream from the remote end, and to analyze it and to generate MOS scores and a range of diagnostic data. And these embedded call quality agents generate the metrics to support the RTCPXR and RFC 6035 protocols. So that's all done internally, and the amount of CPU that these type of agents use is very small. I mean, a small fraction of a MIP, something like 1,000th of a MIP. So it doesn't really affect the performance of the phone at all. RFC 6035 then is the message from an IP phone or a gateway that describes the quality of call from a user perspective, and is typically sent at the end of a call, but the standard actually allows for reporting at intervals or reporting only if an alert condition occurs. But we strongly advise people to use the end of call model, because that doesn't generate too much data, but it does give you sort of a guaranteed way to collect the quality of every call, whether it was good or whether it was bad. And then, as I mentioned, RFC 3611 or RTCPXR allows the IP phone to send call quality metrics to the remote end, and so that enables both voice over IP endpoints to report quality in both directions. So the RFC, these kind of work together a little bit. So the RFC 6035 report can report what it calls local metrics, which are the metrics for the stream of packets that it received. But it can also report remote metrics, which is effectively the quality that the guy at the other end saw, and it's able to do that because if it receives this RFC 3611 message from the other end, then that gives it the information that it can use then to put into the SIP message. So an RFC 60, I've kind of truncated it a lot, but the RFC 6035 report looks kind of like this. So you have a whole bunch of SIP header information above it, And then you have some basically descriptive information about the call itself, the call ID, the phone URIs or phone numbers of the endpoints, the IP addresses of the endpoints. So that allows you to clearly identify who were the two endpoints of the call and what was the call ID. And then you have a local metrics block, and then there is another very similar looking remote metrics block, which is optional, but that gives you the same information from the other end. And so this contains the timestamps, start and stop of the call, the session description information, which tells you things like the codec, the sample rate that was being used, frame size, and that kind of thing. The jitter buffer parameters. So so in this case, the nominal jitter buffer size was 40 milliseconds. And then the packet loss rate. So NLR stands for network loss rate. So these are packets dropped by the network. And JDR stands for jitter buffer discard rate. So this meant that 2% of the packets were discarded because of jitter. And then the burst gap loss. So as I mentioned before, it's important to look at the time varying nature of quality. So what we do is we kind of divide the call up into bursts and gaps. And so the idea is bursts a period of times where the packet loss rate or discard rate was high enough to cause noticeable degradation that would the user would notice, and gaps are periods of time where there may be occasional losses or discards, but it's not really enough to you would never know. And so the burst gap loss is giving you the loss rates and the durations of those bursts and gaps. And then the delay, round trip delay, 200 milliseconds in this case. End system delay, which I mentioned is a combination of encoding and jitter buffer, and then signal level, noise level, and echo level, which may or may not be available in devices. And then the resulting MOS scores, so MOS, listening quality MOS, conversational quality MOS. So that's a typical RFC 6035 report. So if you imagine you have that for every call at the end of the call, then this gives you, a good set of data. So you can start off by saying, oh, the MOS LQ in this case was 3.2. Okay, well, what was going on with that? So RTCP XR contains a very similar set of data, slightly as a subset of that data. And RTCP XR messages are exchanged between the two endpoints every 6 seconds or so. And it basically allows the endpoint to know what the quality was from the remote end. The original idea behind this was that you could use this data to trigger configuration changes. So, for example, maybe you're using a very high bandwidth codec, and the network's not quite supporting it, and so you're getting high levels of jitter and loss and other stuff going on. You could change the codec. It could cause you to change the codec to a lower bandwidth one to see if that helped. But it also allows the endpoint to report quality for both directions using the set message. So a typical passive model is like this. So you have the IP phones on sites, which have the embedded call quality monitoring. So they're able to send the SIP RFC 6035 reports at the end of a call, back up the chain to the management system. And then you could have probes on either probes on sites or probes in the core of the network that are monitoring the calls directly, where they can pick up signaling and media information and report that. And so, if you imagine that a phone on this large site was making a call to a phone on this small site, then you'd have a report from one of the IP phones on the large site. You'd have reports from one of the phones on the small site, and because it went past a probe, you would also have a probe report from the middle of the network as well. So that gives you visibility from both ends and the middle. So you get a good perspective on what's going on with the call. And then what you do is you take this information and you correlate it, and so you display it. And so and the idea behind the typical dashboard approach is to let the user know immediately there's something going wrong. It gives them visibility of what it is, where they can look, what they can click on to be able to drill down and go into the details of the problem. So So basically what we've done is we've talked about the reactive approach, which is less desirable. So we don't really want to have to rely on users to report problems, and because that puts us under time pressure to fix things quickly and people get annoyed. The proactive approach is much better, where we're detecting problems before they impact users, or at least before users complain. Detect problems immediately they occur. We can do earlier troubleshooting with less firefighting, improve service reliability. We can do this with active testing or passive monitoring, or ideally with both. So that's the last slide. So just one quick one on Telcomy. So we're the leading provider of software technology for doing this kind of thing. So for real-time monitoring of voice over IP and video conferencing. We were intimately involved in the standardization work in this area, so we were authors of the RTCP-XR and RSC 6035 protocols and other things. And we have a large deployment in the network, and so there's I think about 500 million copies of the VQMon software deployed in the world. So with that, any questions?
All right. It doesn't look like we have any questions here, but if anybody thinks of one later, please feel free to email us at webinar@vertical.com. We'll make sure that question gets to Alan and that you get all of the information that you need. Alan, thank you so much for presenting. That was really wonderful. I'll make sure that everybody receives this later. You'll get an email tomorrow morning. So have a nice day, and I'll talk to y'all later.
Great. Thank you.